In today's lecture, we will be studying what is equalization. Fourth module 4.2. Okay, 4.2, the second part of the fourth module. In equalization, we will be studying two types of equalization. One is called as linear equalization, other one is non-linear equalization. Under linear equalization, we have zero forcing equalization algorithm, MMSE equalization algorithm. We have adaptive algorithms and we have least mean square LMS algorithm to be an adaptive algorithm for equalization. So let me begin with an introduction to what is equalization. Wireless channels, it can exhibit delay dispersion, fading. So many problems are there when a signal is transmitted from the transmitter end to the receiver. In the previous class, we have seen diversity as a mechanism to overcome fading, right? Similarly, we have a very important problem called as intersymbol interference. We have already studied what is intersymbol interference in our previous sessions. Equalization is going to be a very important technique to overcome ISI. So what are the problems that we might face when we take steps to overcome ISI is what we will be studying in equalization. What are the different algorithms that we are using to avoid ISI? When we try to avoid ISI, what are the other real-time problems that we are going to face? And this particular section in our syllabus is going to deal with all these problems. Okay. So one is called as delay dispersion. You know what is delay dispersion? We have already studied. And delay dispersion is one of the main reasons why intersymbol interference is caused. When a pulse is transmitted from one point to the other, the pulse might interfere with the previous pulses. And while studying communication engineering basics, we have studied what is pulse shaping and how we are going to overcome this in the receiver end with the help of a matched filter. Pulse shaping and matched filter. So this is an introduction to the second section of our fourth module, equalizers. So what are the steps that we have taken to mitigate ISI? What are the three important steps? The three techniques that can be used to improve the received signal quality and link performance over small scale times and distances. First one is diversity, which we have seen in the previous lectures. So first thing what we have studied is diversity. One of the most important ways to improve the received signal quality, right? Second thing is what we are going to study today, that is called as equalization. The third one is called as channel coding. We'll be studying some part of channel coding in the coming sessions. So what is an equalizer? Equalizer is a device that can remove all time delayed waves, and the objective of the equalizer or the equalizer circuit is to remove out intersymbol interference, ISI, completely from the received signal. We know that ISI can cause distortion and there can be a change in the received signal if there is ISI. So equalization compensates for intersymbol interference created by multipath within time dispersive channels. ISI occurs if the modulation bandwidth exceeds coherence bandwidth. Equalization compensates for the ISI, and ISI occurs when the modulation bandwidth exceeds coherence bandwidth. Equalizers can increase the noise power. So what we are doing is that we are basically trying to remove or eliminate ISI, but what happens is that the received signal comes along with the noise. So what happens is that when you enhance the received signal, there are chances that the noise is also enhanced. Equalizers must be adaptive since the channel is generally unknown and time varying. A wireless channel can have indefinite problems. As the wave travels from one point to the other, there might be different kinds of distortions. Okay, the wave travels in multiple paths. So there can be different kinds of distortions. The type of channel or the channel response is usually not known to the transmitter. And it has a very volatile property. That means that it varies very quickly along with time. So we have to keep all these points in consideration while we design an equalizer. An equalizer is usually implemented at the baseband or at IF in a receiver. So we are going to study the details. We are going to study the details of the receiver. Okay, equalization is done at the receiver. So this is a basic block diagram of an communication system. Here, let us consider S of t to be the input signal that is passing through a wireless channel H of f, the transfer function H of f. What happens during the transmission? A noise is added. We'll see what are the different types of noises also as we go on, but not in detail because we do not have it in our syllabus. After that, we receive a signal called as y of t. This y of t is passed through the equalizer so that we get s of t plus n of t. Y of t is nothing but s of t plus n of t. Here I am using it as n dash of t because there is an enhancement in the noise when it passes through an equalizer. And then it is demodulated and processed. So now this is an introductory slide where I am telling you what is the input, what is the channel response, and so on. So let us consider a signal, input signal S of t passed through a channel with frequency response H of f. At the receiver front, we expect a white Gaussian noise N of t is added to the signal so that the input at the receiver will be in frequency terms or in frequency domain. Y of f is equal to S of f, H of f plus N of f, where N of f is the white noise with a power spectral density N0 by 2. It's almost a standard definition and we are using it in every places. The received signal y of f passing through the equalizer becomes, here what it is happening, S of f is the input signal in frequency domain, H of f is the transfer function of the channel, noise N of f through the equalizer. Equalizer transfer function, here we are defining it as Heq of f, and this will be nothing but S of f plus N dash of f. That means that the noise is enhanced. This means that the noise is enhanced. So n dash of f is colored Gaussian noise with power spectral density 0.5 n naught by hf square. Thus, what happens is that after passing through the equalizer, the intersymbol interference from the received signal has been completely removed, but there is an enhancement in noise. Okay, it is removed because we have what is called as HEQ of F. Okay. So here I'm defining, or here I'm giving a basic block diagram of different types of equalizers. Okay, equalization techniques can be broadly classified into two. One is called as linear and the other is non-linear. Okay, two things, linear and non-linear. Based on the structures, we can classify linear and non-linear into transversal and lattice. Both linear and non-linear equalizers have this classification, transversal and lattice. Further, non-linear equalizers can be classified as two. One is decision feedback equalizer. The other one is MLSE, maximum likelihood equalizer. MLSE. We have LMS, least mean square algorithm, which we will be studying in the next session. We have RLS algorithms. So these are all adaptive algorithms that help us to improvise the noise. So non-linear structures are of two types, DFE and what we have seen in the previous slide, MLSE. So linear and non-linear equalizers are typically implemented using two structures. One is called as transversal and the other one is called as lattice structure. The transversal structure is a filter with n-1 delay elements and n tabs featuring tunable complex weights. So what is a transversal filter or a lattice filter? The reason why I have included this slide in your class is because I'm just expecting some questions in 3 marks about what is a transversal structure or what is a lattice structure, or differentiate between transversal and lattice structures. Okay, so a lattice structure uses a more complex RLS algorithms. Okay, for this increased complexity, what we have is that we have numerical stability and convergence properties and a greater flexibility in changing their length. So if you could write down these points in your exam when there is a question about what is the cost that you have to pay for a lattice structure which is more complex, you can write this. What is the advantage of lattice structure over transversal structures in equalization? When you get questions of this sort, you can answer this only with these points. This is a very important block diagram. Today's entire session and tomorrow's entire session I'm going to explain to you with the help of this block diagram. So it is very important for you to understand this block diagram, and if possible absorb it in your mind also, so that whenever I'm explaining to you, you can recall it. Is there anybody with a good pictographic memory? Take photographs of this particular slide with your eyes and store it in your mind so that you can reproduce it at several places. So let me explain this block diagram. dk is the input signal that is passing through a pulse shaping filter with a frequency response g of t, and it passes through an channel which causes intersymbol interference. We call the channel response to be c of t, and the combined input, that is h of t, is nothing but is defined as g of t convolution c of t. When it passes through this wireless channel, you have a noise added to it, and from there it is being received at the RF front end. We have seen that when we have a pulse shaping filter at the transmitter end, we will be having what is called as a matched filter at the receiver end. The response of the matched filter is given as gm minus t, gm of minus t, and the signal received here is w of t. The output y of t is received, and then we are sampling this received signal into n samples. So we are taking it as y of n. This is given as an input to the equalizer. Then we have a decision device, and the equalizer will be having a transfer function of h eq of z. Okay. Now this will be further explained in the coming slides so that you will be able to understand it very clearly. So the input signal d of k is passed through the pulse shaping filter with a frequency response g of t, and then transmitted over an ISI channel with equivalent low pass impulse response. Whatever algorithm you are asked to explain in the examination, you need to write all these things. So after the signal passes through the white Gaussian noise, we have this power spectral density of white Gaussian noise to be n0 by 2. This is added to the received signal, and the resulting signal is W of t. So what happens to Wt? This is where we are going to give the input to the equalizer. This Wt is passed through the matched filter to obtain a low pass equivalent called as y of t, which is further sampled to obtain y of n, and this is what is being given as an input to the equalizer. So now we are defining f of t as the composite equivalent low pass impulse response consisting of the transmitter pulse shape, channel, and the matched filter impulse response. Okay, so f of t is defined as g of t, the pulse shape, the output of the pulse shaping filter, channel response, and the matched filter. We are combining all these responses to call it as FT. So the matched filter output will be given as y of t is equal to d of t. D of t is the input, f of t plus the noise ng of t. I'll tell you why I've used a different notation, ng of t for noise, and this will be equal to sum of all the symbols dk f of t minus k ts. Suppose we are taking the kth symbol plus ng of t. So n of t is nothing but ng of t is nothing but n of t, the noise, the signal along with the noise is given to the matched filter, and so you have an change in the noise, right? Yes or no? So n of t convolution gm of minus t. This is the response of the thing that is given here. This is the response of the matched filter. Okay. So ng of t here we are defining it as the output of, after this signal reaches the matched filter, the output is taken to be y of t, right? So it includes the matched filter response also. Of course, sampling time or the symbol time ts is the symbol time. Over. So, as discussed earlier, y of n is the sampled signal, which is nothing but y of n ts. So the discrete time signal which we are giving as a input to the equalizer is y n ts. So when we substitute this from the previous slide, y of n will be nothing but dk f of n ts minus kts plus ng of n ts. We have to note that we have seen two parts, right? G of t. What is G of t? G of t is the response of the pulse shaping filter, right? Pulse shaping filter we have control. We are designing the filter. But the channel we don't have any control, right? The channel is time varying and is highly volatile. Now, what are linear equalizers? The next topic in our syllabus is linear and non-linear equalizers. We are studying what is linear equalizer. A linear equalizer can be implemented by an FIR filter or a transversal filter. As we have seen previously, we have two different types of structures, transversal structure and lattice structure. So linear equalizers The most important advantage is that they are the simplest form of equalizers available. There is no need of any complexity. In linear filters, the current and the past values of the received signal are linearly weighted by the filter coefficient and summed to produce the output. So what happens is that it is linearly weighted. That means there is a big disadvantage coming up. That means that even the noise is being enhanced, right? So there is a disadvantage of linear filter. Linear filter advantage is that it is the simplest one. The disadvantage, the most important disadvantage, as we have already discussed, a linear equalizer places too much gain near the spectral null, thereby enhancing the noise present in the frequencies. So what is a linear equalizer? Draw the block diagram of an linear equalizer. The transfer function of of a linear equalizer of length L, which n taps, n minus 1 taps, is given by n is equal to L, 2L plus 1. The equalizer response is nothing but Heq of t is equal to sigma I is equal to minus L to L Wi Z minus I. Here is where you are going to study one of the most important applications of Z transforms. I hope all of you remember what is Z transform, which you have studied previously. We know that the performance of a wireless system is measured by two important parameters. The first parameter is nothing but the outage probability, and the second parameter is the probability of error. So here our job is to find out Wi in such a way that ISI is eliminated. Okay, we are going to study a set of algorithms called as zero forcing algorithms, and then MMSE algorithms, LSE algorithms. For all these algorithms, what we are going to do is that we are going to find out the optimal value of Wi so that the equalizer is able to eliminate intersymbol interference. The equalizer design must specify two important criteria. One is the tap weights. So in order to design an equalizer, you should have to define two specifications. Specification means how your equalizer should perform. So your equalizer should contain two important things. We are going to find out what is Wi for different types and an algorithm which is going to be highly adaptive because the channel keeps varying. So two types of linear equalizers mentioned in your syllabus are, first one is zero forcing and the other one is MMSE, minimum mean square error equalizer. These are the two types of linear equalizers. We are going to study its design. You may be asked problems. You may be asked to design equalizers. You may be asked to explain the steps taken. and so on. You may not understand this importance right now, but as you go on, you will be able to understand how important it is, provided all of you listen to me very carefully. Coming to what is zero forcing algorithm or zero forcing equalizers. Studying what is zero forcing equalizer. In a zero forcing equalizer, the equalizer coefficients are chosen to force the samples of the combined channel and equalizer impulse response to zero at all but one of the spaced sample points in the tap delay filter. This form of equalizer was first proposed by Robert Luckey. You can search in Google Scholar for the research work what he has done. You can study the paper. So what is zero forcing algorithm? So the samples y of n is the input to the equalizer, okay, and is based on the discretized combined equivalent low pass impulse response. So here we are going to define f of t as we have defined previously. F of t is h of t into g of minus t. Y of n is the sampled input to the equalizer. Y of n is the received signal and the output of the masked filter. You remember the block diagram which we have studied now? From the masked filter, what we are doing? Masked filter. The output is further sampled. So you get y of n. This is the output here, y of t. Okay? So zero forcing equalizers. We have already seen that y of t is equal to the input to the equalizer. Y of t is equal to d of t into f of t. F of t is the combined transfer function of the pulse shaping filter, channel response and the masked filter, and then plus noise. We have already seen that f of t is the combined response of pulse shaping filter, the channel response and the masked filter. In zero forcing algorithms or zero forcing equalizers, we take the Z transform of this particular input. This is an algorithm we are going to design to eliminate intersymbol interference. So now let us take the Z transform. Y of Z is equal to dz, d of z, f of z plus ng of z. Is the ng of z is the Z transform of ng of t. At the output of the masked filter, the masked filter frequency response is given by Gm convolution 1 by Z convolution or Z conjugate, I'm sorry. Gm conjugate of 1 by Z conjugate. Gm is the transfer function of the matched filter. So let us now find out what is f of z. F of z is given by F of z is equal to h of z gm conjugate 1 by z conjugate, that is equal to, for n taps, sigma n f n ts. You are sampling this n times, z raised to minus n. You are finding what is f of z. Our objective is to find out Heq of z, right? What is Heq of z? The equalizer transfer function. Am I right? So this is the input to the equalizer. So f of z we have written. The zero forcing equalizer now removes all the inter-symbol interference introduced in the composite f of t. So we need to have a transfer function called as ZF. ZF stands for zero forcing algorithm or zero forcing equalizer. ZF of z, that is equal to 1 by fz. With this we are able to prove that a zero forcing equalizer can eliminate all the inter-symbol interference. So this is the transfer function of the equalizer, 1 by fz. What is fz? Fz is nothing but the combined response of Z transform of the combined frequency response of the pulse shaping filter plus the. Are you able to understand what I am saying? If you listen here, you can carefully, you can very easily understand. See, in zero forcing algorithm, what we are having is that we are having, first we are having a pulse shaping filter followed by the channel response, which we do not know, and then we have a masked filter, right? Yes or no? So this channel is causing inter-symbol interference. What we are going to do is that we are going to use the inverse of all the combined three transfer functions in the equalizer. That is what is called as f of z, right? We are taking the z transform of the combined values of all the three transforms, and then we are just inversing it 1 by. Now ISI will be eliminated. Can you understand how it is eliminated? All of you understood how inter-symbol interference can be eliminated? You are taking the inverse of all the combined transfer function responses. So what you are supposed to get is nothing but the input signal without any ISI plus the noise. Noise is certainly there and noise is enhanced. Okay. If the noise increases, what happens? The performance of zero forcing algorithm degrades. Am I right? Yes or no? Understood all of you clearly? Do not. So we have completed what is zero forcing algorithm. Now we'll be studying the next type of equalizers called as minimum mean square error equalizers. MMSE. Like the previous zero forcing algorithm, our objective is to eliminate inter-symbol interference. So we are doing this by minimizing the average mean square, which is called as MSE, between the transmitted signal symbol dk and its estimate dk at the output of the equalizer. So the weights Wi, that is, we have seen that Heq is equal to sigma minus L to L Wi into Z minus I, right? Yes or no for linear equalizers? Now what we have to do is that we have to design the weights. Wi must be so chosen that the error for a MMSE, that is minimum mean square error equalizers, we are going to choose Wi so that E dk of dk tap the square tilde dk, that means that this value, this is the error function, this is the input dk, this is the thing at the output of the equalizer. So we want to make it in such a way that this dk minus dk tap or dk tilde should be as low as possible. That is our objective. That is our objective in minimum mean square equalizers. So since this MMSE equalizer is linear, the output dk should also be linear and should be a linear combination of the input is y of k, right? K or n or whatever is the number of samples you are taking, right? So here the output dk is nothing but I minus L to L Wi y of k minus I. So this is a block diagram of an MMSE equalizer. Here what we are doing is that we have the rest of the things seems to be very similar to what we have done in the previous block diagram. That is block diagram, it is not specifically for zero forcing, but all kinds of linear equalizers. Here this is a specific block diagram for minimum mean square error equalizer. In this what we see is that we have two important components. One is called as the noise whitener and the other one is called as the HEQ of Z, right? So what it means is that the output of the matched filter is a colored noise, is not a white noise. So what we are going to do is that we are going to add a white noisener, it's a noise whitener, to remove out the colored part of the noise and make it into a white noise. And then we are going to pass it through a equalizer so that we get the necessary output where we are going to remove out our intersymbol interference. So we have two important components in our MMSE. The first component is the noise whitener. The noise input to the equalizer is not white but a colored one because of the transfer function of the matched filter, or because of the presence of the matched filter, where we have this GM conjugate of minus T here. So we need two important components, two important parts we have. That is, one is called as the noise whitener and the other one is the ISI removal component. So for very simple, for noise whitener what we can do, we can create a filter because the power spectrum of the noise component is given by N0 by GM conjugate 1 by GM conjugate of 1 by Z conjugate the whole square. So you simply multiply by this, what will happen is that you will get something like this now. This N0 by GM 1 by Z the whole square by this path 1 by GM. So this both things will get cancelled and we'll get N0, right? That is what we wanted. So noise whitening filter will have the transfer function of the inverse of the component which is making it colored. That's it, right? Yes or no? So what is making it colored? Matched filter response. Just take its inverse, you get it as white. noise. Am I right? Like what we have done in the previous one. So now this linear equalizer, we have seen already that this transfer function of the linear equalizer will be something like this, right? H eq of z will be minus L to L Wi Zi, and here our objective is to find out this optimal value for Wi so that we do not have any intersymbol interference, right? Yes or no? So now the goal of this filter is to find out the optimal value of Wi so that dk minus the error, the estimate or between the dk and the output of the equalizer dk tap is as low as possible. Okay, is minimized to a very optimal level. E of dk minus dk tap square is minimized to the lowest possible value. Now in that case, what we are going to do is that we are going to define a component called as j, which is equal to this particular value, which we are going to minimize, right? Now in this, what we are going to do is that we are going to substitute the value of dk. We know that we have w and v here, and this is the output of the equalizer, right? Yes or no? This is the output of the equalizer, which is the real part of v. We take it as a Hermitian matrix v of h. Okay, so that what we get is j is equal to the value that we are trying to make it as low as possible, right? And then we are going to substitute it with the values what we have already found out, right? We are going to define Hermitian matrices. So the color spectrum, the output will be N naught by G, right? Now we are going to define two different matrices. MV that is equal to E VVH and VD that is equal to E VH dk. So MV is an n cross n Hermitian matrix and VD is a row vector matrix of length n. Let us assume that E of dk is equal to 0. From the previous slide, we know that J, the value that we are going to minimize, J is equal to E of W transpose. That is the thing that is received before the matched filter, right? V the noise component, VH W star, W conjugate. Now this V into VH, we are defining it as MV. So we get this MV here. Okay. The next part is this is minus the real part of VH W star dk, right? In that VH and dk, we are substituting by another value called as VD, right? And we are assuming that dk is equal to 1. And then we are substituting these values in the equation that we have seen previously. So now, in order to find the optimal value, we call it as W opt, okay, or omega opt. what we do is that we find out the gradient. Gradient given by gradient omega j. We are setting this value to 0 so that we get the optimal value for W, which is our objective, right? Yes or no? And this value, what we are doing is that we are setting this value to 0, is equal to 0. In that case, what we'll get? We'll get W transpose MV is equal to VD, right? Yes. When we set this to 0, you will get this value, right? Yes or no? So here you are able to find out the optimal value of W here. So the optimal value Wj is set to 0. So we'll get Wt Mv is equal to Vd. Therefore, the optimal Wt, W is nothing but Mv transpose inverse Vd of T, Vd transpose. So now what we are going to do is that we are going to solve for W opt. As such, solving for W opt requires very complex operations. So what we are going to do is that we are going to find out the minimum value J min, which is defined as 1 minus Vd Mv inverse Vd Hermitian H. From that, we know that already that equalizer function now Heq is Wi Zi minus L to L. So here for Wi we are substituting this value. Let us consider an equalizer with infinite length, that is we are giving minus infinity to infinity here, and we are finding out Wi Zi. So we are substituting for the equalizer Heq of Z. So what is Wi? Fi f of j minus I plus n naught into delta j minus I is equal to gm of j. So we'll take the Z transform of what we have done previously. Taking the Z transform, you will get H equalizer is equal to f of z plus n naught, which is equal to jm of inverse of z conjugate. So what is that? So we are going to find out the final one. The output of the noise whitener is given to the equalizer. That is what is given by Heq of z. So consists of the noise whitening filter Jm, the total filter. So Heq of z will be nothing but H cap Eq by Gm conjugate 1 minus z conjugate. The equalizer of an MMSE, the transfer function of an MMSE equalizer will thus be defined as Heq of z, which is equal to 1 by f of z plus n naught. So what we learned from this is that the ideal infinite MMSE equalizer cancels out the noise whitening filter. If you have an infinite filter, what happens? The noise is getting, or the noise whitening is not required, right? Yes or no? Second thing what we need to see is that these might be questions in your exams, so you have to be very careful when you write. An infinite length equalizer will be somewhat similar to what we have studied in the previous slides, that is about the zero forcing equalizer. Okay, except for the noise term n naught. So in the absence of noise, both the equalizers have almost the same working principle. Yes or no? The third and the final point is that an ideal equalizer shows a balance between inverting the channel and the noise enhancement. We have seen that zero forcing filter reduces the eliminates ISI completely but enhances the noise, right? Yes or no? So with this we have completed a very small part of 4.2 equalizers. We have to study another algorithm called as least mean square algorithm, LMS algorithm, which is a nonlinear adaptive algorithm for equalizers, which we will be studying in the coming sessions. Thank you all. Thank you very much for listening to me.